welcome our next speaker, Steve White from UCL.
Well, I've never cut it this close before, not by an order of magnitude, I think. Usually I'm, there a day or two before, and but this was such a nice flight. Left at 7 o'clock. Took off. I left my house at 7 o'clock my time this morning, so it was very nice to fly here with just a certain risk. And have you all heard of Uber time dilation? That's when you call up Uber and it says the car will be here in 10 minutes. And then you wait 5 minutes and it says it'll be here in 9 minutes. And that keeps happening. And then I even had just a little bit of Uber time travel where instead of 9 minutes, it says 15 minutes. But so it's good to be here. This is designed to be sort of an introductory talk. It's designed for the third-year graduate student level, perhaps. So some of you may have heard about it, but hopefully I'll have some more jokes and you can enjoy the presentation. But it's designed not to overwhelm you with details, but just to sort of give you the big picture in ways which you can remember. So this is the introduction to tensor networks. We'll get a little bit into DMRG and nothing too fancy for this lecture. And this lecture will be sort of slow and ask lots of questions. It's, so everybody follows along pretty easily. And then the next lecture, I'll have a little bit faster pace, a little bit more recent stuff. Let me just start off then and say that our key problem in what we do is the exponential complexity quantum mechanics. Quantum mechanics is just too big. Qubits have 2 to the n, different possibilities. And so the question is, what do we do with that? And of course, there are various treatments, sampling methods with quantum Monte Carlo, various other things. The key idea of sort of all that we do is that the physics that we're interested in doesn't really care about all of that pure exponential complexity. If you want to look at an area that uses that exponential complexity, think of cryptography. We know something about that if you've heard of Shor's algorithm. It purposely tries to scramble everything up, use the whole Hilbert space. It's a mess. You can't do anything with it. It's unpredictable. Okay, so the way I like to explain tensor networks is to just think about it in terms of the idea of compression. And by compression, I don't mean squeezing material, but the same thing that you do to a file. You zip it up, and if it's random data, I don't know if you've tried this, but it doesn't compress at all, particularly binary data. If it's ASCII data, could compress a little bit because the ASCII code is got a little bit of inefficiency in it. But you have to have some sort of simplification of what you're doing. And so our hope for doing physics beyond the sort of 10 or 20 site exact diagonalization has to rely on some sort of simplicity in what's going on, in the physics of what's going on. And it may be that this only applies to certain aspects that we might look at. Certain things may be compressible and certain things may not be. So let's think about compressing, say, a matrix, okay? And this is an old topic, and the simplest way to compress a matrix is just sparsity, where many elements are 0, and you only keep track of where the non-zero ones and store those. And a lot of quantum mechanics is very sparse. And so that's a useful idea, but it's not really the main thing. So there's this other idea which you see throughout lots of different areas of modern big data and numerical analysis and physics, is the idea of low rank. Okay, so we have a huge matrix and we want to compress it. Maybe it's exponentially large. Okay, so the idea of a low rank matrix is that it's something, and let me just sort of draw this as sort of a sketch to give you the idea of the size. It's the product of two matrices where they're rectangular matrices, and there's a big difference in the size between the two parts. And so you're going to express the big matrix as the product of these two. Now, if it only goes half the size, then you're not going to get anything because you have to do two matrices. Okay, but it could be that this is a huge difference. And when you're dealing with exponentially big problems, you have the opportunity to get an exponential compression. Okay, so this sounds like a great thing. It turns out it's gone, but how do you know if you have something that's compressible? And the standard approach to do this, numerical approach, is the singular value decomposition, the SVD. Okay, so the SVD is a lot like a diagonalization, but you know, the representation is more general, and in fact, it'll work for rectangular matrix. So it's a factorization where we have an arbitrary matrix M, doesn't have to have any properties, doesn't have to be Hermitian, we don't care. It's a U times D times V. And sometimes they put a transpose or a dagger on the V. I won't worry about that. Okay, so it's a factorization, and it's unitary times diagonal times unitary. Okay. So, and it's unique up to, you know, a few minus signs. The diagonal elements are positive or 0. Okay, and so it's a very friendly guy. You can do it with any matrix. And the key thing that you can tell if something is low rank is that the eigenvalues in the D matrix will be 0. So the D has singular values, they're called lambdas. And if they're 0, you get to throw them out. So they give them to you sorted. And if you find out that your big matrix just has 10 or 100 non-zero of these things, you can throw away all the rest. And that, if you think about how these multiply, matrix multiply, it immediately gives you rectangular matrices, and it immediately gives you this very compressed format. And if they're truly 0, then it's sort of lossless, it's for free. Okay, now what more typically happens is that there may be some reason that the singular values will decay, say, exponentially, or some sort of rapid fall off. Okay, so then you have to choose your accuracy, and you put a cutoff, and you say, I will truncate these things. Okay, so this is used a lot. I was at a conference with lots of postdocs giving posters last summer. And it was at CCQ. It was a little bit numerically oriented, but it seemed like about a third of the posters had low rank in the title. So it's a very common thing. Okay, it's very useful, you know, shows up in different areas. Okay, so this is a way, and this is the heart of tensor networks, that there are hidden low rank matrices throughout. And they allow us to compress things, and then we need to be able to work with things in this compressed format. Okay, so before I go any further, let me introduce a little bit of our tensor diagram notation. Okay, and this is really simple. It's, you know, it's a little bit like Feynman diagrams but much less complicated. Basically, if we have a matrix Mij with indices I and j, we just draw it like this. And we can label them if that's important, and I and j. And so we just take the external indices that are on the object and we draw them coming out from a dot. And then suppose we wanted to multiply some matrices. So m times n. Okay, so the result is going to be an ij. That's the index of the result. Diagrammatically, that looks like this. Okay, and we can put the I and the J. Okay, and of course, the form, the summation for this is sum on K, MIK, NKJ. Okay, and so there's you can see that there's an internal link in this, which is K, and K gets summed over. And it's a dummy variable, so we don't care about it. So there's no point in putting it in our diagram. And so it gives you a nice notation for matrix multiplies. Doesn't buy you too much for matrix notation. The algebraic notation is good, but when you're doing tensors, it's great. And you know, a little bit of history back in the early days of DMRG, before it was really tensor networks, we were doing matrix product states in algebraic notation without any diagrams. And then one of the nicest things that came along when people from quantum information sort of merged into condensed matter computational things like DMRG is that they immediately brought over diagrams, you know, with their close connection to quantum circuit diagrams. It was sort of natural, and it made everything easier to think about. Okay, so a vector looks like that, and then a typical tensor with 3 legs looks like that. Okay, so a wave function. Okay, so let's think of spins. Okay, so a wave function, the thing that makes them difficult is they have a lot of legs. Okay, so there's a wave function, and it's just psi of S1, S2, up to Sn. So a lot of legs, and so that's what makes it exponentially difficult. Okay. Okay, so the key insight is, and you know, okay, so I can draw it like this, but usually when you learn quantum mechanics, you say, oh, the wave function is a vector, Hamiltonians are matrices. But for any system with more than, say, 2 spins, you can think of it as a matrix. Okay, and how do we think of it as a matrix and not a tensor? Okay. We just have to group together the sites. Okay, so a pretty simple thing is this grouping together of degrees of freedom. You know, if you have 2 spins, you can think of it as 1 index that goes over 4 values. It's lossless. And so we can group things and make this into a psi ij. So the grouped index is I and the other group is j. And I have to decide how I want to divide up the sites. I assume that I always put them either into the I or the j for this part. And so how many different ways are there to do that? Oh, well, it's some sort of exponential. It's a lot of ways, a lot of terrible ways to do this. We only need one good way where we get this compression that's really good. So we don't care if there's sort of an exponentially large number of ways of dividing this up in bad ways. Okay, so the idea then is that we can say this is psi ij, and maybe this has an SVD, UDV, and it turns out to be low rank. Okay. So why would it be low rank? And so, of course, this goes back to the idea that things are simpler than you thought. The thing that makes, so many methods, have some simplicity built into them. A thing in favor of tensor networks is that it's more general than most methods. It relies, it's not specific to spin systems. It works for fermion systems. It works for general systems. It works for lots of different things. Pretty general. And the idea that it uses, and of course, it can't work on random data. And if you ask a mathematician or a worst case complexity analysis, they'll come up with some terrible cases. But the Hamiltonians that we're usually interested in are very simple, not exponentially complicated. So why does this work? I'll just say why. Okay, so first of all, H is simple. Okay, so you say, oh, my H isn't simple. It has 4 particle terms or something. Okay, we think that that's hard, but it's not 100 particle terms. It's not n particle terms where n isn't, that's complicated. That would give you exponential complexity. Okay, so the Hamiltonian is extremely simple on the exponential scale. And then the other thing that comes along is that if you, what we're doing, and say we want to find the ground state, is that minimizing E is simple. Okay, so what does that mean? Well, basically we're telling it, oh, pay attention to the Hamiltonian. Do what it tells you. If you just think about a simple analysis, oh, try to do what the Hamiltonian, solve some little part of it, put it in that ground state, do that for some other parts. That sort of gets you in the right direction, okay? And so these two things together give us are sort of at the heart of the compressibility, and it brings in the idea of entanglement. So let's think of the simplest type of entanglement. So let's say we had a Hamiltonian S1.S2, okay? And so that's a Heisenberg Hamiltonian. We got a spin here and a spin there. What's its ground state is the singlet, 1/√2, up, down, minus, down, up. Okay, that's the singlet. Okay, what's it done? Well, it's taken these 4 degrees of freedom, and if you solve this, it's given you one unique ground state. Okay, and an important thing is that once you have a singlet, if there's a singlet, singlets don't entangle. Okay, they don't entangle at all. Okay, so this is related to the concept of monogamy. You know what monogamy is? You're probably thinking, oh yeah, in my topology class, didn't we just not quite get there, or did I forget it? No, monogamy is where you're married and you don't mess around with anybody else. Okay, that's monogamy. Okay, so singlets, 2 spins, they don't mess around. And why is that? It's because it's a singlet, there's only one state. If there's only one state, it just can come out as essentially as a scalar. Nothing happens. It just sits there. All it can be is in a product state with anything else. Entanglement has to be where you have 2 possible states or more that's fluctuating with another one. Okay, and then you can get entanglement. If there's only one, it just sits there. Okay, so as soon as you get states that are forming singlets, the entanglement, when you look outside of those 2 guys, goes down. So we can draw a picture of sort of a typical, say, 2D spin system. Okay, so there's lots of spins there. Okay, and let me draw a dividing line between them. Okay, and what's the dividing line? Well, it's really one system, but I want to think of dividing the system into two different parts for the I index and the J index for the SVD. Okay, so it's an artificial partition of the system, and I put spins on either side. Okay, and so there are some spins, and they have this nice friendly local Hamiltonian, and a lot of them are going into these singlets. Okay, and the same on the other side. Okay, so in terms of this SVD, these guys totally drop out. They just sit there and nothing happens. And then there are some spins that are entangled across the boundary. Okay, and maybe if it's all dimerized, if it's all perfect, you could draw a line that doesn't cut any spins. But normally these things fluctuate. And so this is our cartoon picture. And we think of it, oh, it's fluctuating. It's not a totally trivial ground state, but we can think of it as being largely made up of entangled spins fluctuating around. And this is the RVB state, the very famous RVB state that dates back to Pauling and then was promoted by Anderson. And it can be a very general representation, or it can be a good sort of approximate ground state. Okay, so if you have these fluctuations, you can sort of think of these parts, but whatever way you think of it in an instantaneous picture, there'll be parts of this that are just on one side and they're not entangled. And so you get little entanglement. And so if we look at the rank that you get in this sort of situation, the size of the little matrix in the middle, the rank will go as roughly e to the area. And the area is, in this case, it's just the length of that line, because you want to count up sort of on average how many of these links will cross. Okay, and so the rank will sort of pay attention to that, and it has to keep track of all the degrees of freedom on each side of the line. And so it just multiplies up by the number of degrees of freedom, say 2 for each spin, and the number that get cut. Okay, and this corresponds to an entropy, an entanglement entropy, S, which goes as the log of the rank. Okay, probably most of you know the definition of the von Neumann entanglement entropy. But basically, we just think of it as sort of the log of the number of pieces of the wave function, just like an ordinary entropy. And so this is called the area law. Okay, so this goes, S is proportional to the area, and this is the area law. Okay, so the area law is a very important concept. It's a law, which means it's not proven for the most part, except in this case, it's proven in certain circumstances. But, it's like Hooke's law is sort of just a Taylor series expansion for springs. It's not as good as a theorem. Theorems are better. This is only a law. So it's something that is approximately true in lots of cases for ground states. Okay. Now, what happens if you don't have ground states, if you have excited states? Well, things get much more complicated. And I have, when I show you some slides a little bit later, I'll show you an example of excited states. But there are exponentially many excited states. So they can't all be low. They can't all have a small amount of information in them. There's exponentially many of them, then they have to be extremely complicated. And the area law is gone. Okay. Okay, so this gives us the idea of matrix product states, the simplest form of the tensor network. Okay, so I've tried to motivate that if you took this, and maybe you just do it from an exact diagonalization and you cut your system in two, and you find that it has low rank. How big a rank? We're talking about 10 to 100 for a simple spin chain. So really exponentially smaller or just a small size rank. And so what kind of compression do we get in this? So we get a 2 to the n that goes, if we think of this, okay, this is a little bit early, but sorry, that's a little bit early. Okay, so matrix product states. So I'm going to think of doing this to a ground state. Okay, so to pay attention to what the Hamiltonians are telling me, I want to pay attention to the entanglement and put the stuff on the same side that are, interacting strongly to the Hamiltonian, which normally just means physical locality. You want to cut the system in two. Okay, so you cut it in two and you do your SVD. Okay, what do you get? Okay, so we cut it in two, and then this this middle matrix can be truncated to some small bond dimension. It was 2 to the n over 2, cutting it in half. We sort of, taking the square root of the weight. So we cut it down to some very small number, and then we'll further simplify this just by saying it will absorb the dot into, say, the right-hand side. I'll put a tilde on it, so it's got the dot inside it. Okay, so we factored it into this low rank approximation. What have we gained? Okay, so here we get a 2 to the n. If we split it in half, it's gone to a 2 to the n over 2. And that's an exponential improvement in the amount of data that we have to store. But it's like a square root of the number of degrees of freedom. It's not nearly as good as we would want. We want a real exponential improvement so much that it takes away all the exponentials. So we do it again. Okay, so we take one piece of that and we do it again. And the same ideas are going to apply to this piece also. So this is going to be equal to that, this. Okay, and if we cut those two pieces in two, we've dropped it by sort of another square root of the total number of degrees of freedom, but we keep going. There's nothing interfering with doing this all the way down to the individual site, and you get a matrix product state. Okay. So what is our compression now? We've got 2 to the n has gone over to, okay, so how many matrices do we have? We have n. Well, they're really 3-leg tensors, but you can also think of them as matrices, just like the poly-spin matrices or matrices with an extra index. But they're some matrix dimension squared. Okay, and then there's the degrees of freedom on the top, which I'll just say is another 2 for a spin 1/2. Okay, so this is a great exponential compression. Now we can work with it. And what is this m? So m was the rank, and so we call m the bond dimension, and the other standard notation is capital D for exactly the same thing. And m goes as e to the area of the cuts that you make in going through the system. Well, I have it totally chopped up. So you think of all the possible cuts that you do. You put the sites, so we're thinking now of a 1D system. We put it in a line and we think of all the cuts that you make. It's gonna depend on the worst case. Where's the worst cut? The biggest effective area, the biggest entanglement across that. And that's what's going to control this. Okay. Okay, so that's a matrix product state, and it's very useful, and it's useful, not only for numerical approaches, but also for analytic approaches I'll just be focusing on the numerical approaches and thinking about finding the ground state. Okay, so what do we know so far? So if you gave me the ground state, I've shown you how we can repeatedly do these SVDs. It's a very short little program to do this. It's just exponentially expensive. But we can do these SVDs and turn it into a matrix product state. Okay, so we know how to do that. So we want to use this, and we know the ground state is of this form. But how do we get that form without solving the problem for the ground state in the first place? It's sort of, we haven't really gotten there. It's sort of like a chicken and egg problem, where our egg is huge, but we can use it to make our chicken. Which came first, by the way, the chicken or the egg? Know the story? It's supposed to be a deep philosophical puzzle, but it has an obvious answer. The egg came first because dinosaurs has eggs. Of course, now they say that chickens are dinosaurs, but earlier dinosaurs, right? But there's a hint of beyond the joke in this, which is, how did they really arise? They arose through evolution. And so what did you have a long time ago? You had a really bad chicken and a really bad egg, and they slowly evolved to get better. Okay, so that's the clue to what we want to do. We want to start with a bad chicken and a bad egg, and repeatedly make use of our SVD to shrink things down, and solve. The other part of it is solving the Schrodinger equation at the same time. Okay, so we repeatedly solve the Schrodinger equation. We keep everything in matrix product form. Okay, and we gradually try to evolve to the ground state. Okay, so how do we do that? Okay, so there's a general technique. You can think of this as just a minimization problem, and a lot of people explain it that way. But if you think of it that way, you're likely to devise a very bad algorithm. So there are a lot of bad algorithms, but an example of a bad algorithm, in my opinion, is gradient descent, which consumes most of the electricity in the world, maybe, some huge amount, because that's how you optimize a neural network, right? But it's because they don't have anything better, okay? And in the land of tensor networks, you have something much better, okay? So the general sort of technique I'll call, so we want to do a reduced basis Schrodinger equation, or diagonalization. Okay, so the first part of the idea is that if we have a big Hamiltonian matrix, so this is H, and we block out a little piece of it, so this is H small. Okay, then E small is greater than or equal to E. And this is the ground state energy. Okay, so that's just a variational principle. You do E small in this little piece, you get some approximate wave function. The evaluation of it in terms of the big matrix is the same as in the small matrix. And so what it thinks its energy is just by the variational principle has to be bigger than the true ground state. So it's a way of getting there. So what you can do is you can say, I'm going to use that, and I'm going to try to build that into a further step. And to do that, we want to think of an H tilde, which is rotated. Okay, so let's do a unitary transformation. That's fun. And rotate a Hamiltonian. And this has the same eigenvalue. Oops. What's it doing? Okay, so that's a one-line calculation. So the approach that we want to do then is cleverly choose rotation and cleverly do little diagonal things. So if the rotation, that gives you an H tilde, then we can do this little thing on H tilde and get an H tilde small, okay? And the key thing you want to do is you want to build your ground state from the first one into your U of that gets you to the next one, so that it's already there. Okay, so you build psi ground state small into U, which basically means it needs to be one of the vectors of U, and that one in the part that you keep, and then you can successively improve. So it's an idea. You know, it's not a fleshed out idea because it's problem specific. Okay, but it's a very general approach that can eventually get you to the ground state. Okay, so how do we apply that here? We do our wave function. Okay, and so I divided it up into 3 different parts. And so this is a matrix product state. So to get each part, I can think of just multiplying the tensors in the boxes together and forming a tensor that's a sort of joint tensor. So that's easy to do. Okay, this then, I think of my small piece as defined by this object in the center. Okay, this lives in H small. Okay, and it depends on which sites I do. So I pick some sites. This guy lives in a basis. So the basis, well, what defines your basis? The basis is defined by these boxes and all the tensors that live on the outside. Okay, so whatever those are, those define a rotation. It gives you and a truncation at the same time. So it gives you sort of your definition of your small environment. And if you ensure that those are unitary, which is not hard, then it exactly fulfills this. And you can solve your small problem and know that your energy is going to be a variational bound to the exact energy. Okay, and so you do this. Okay, solve the Schrodinger equation for this. Okay, and there's a particular reason that we put 2 sites in the middle. The reason is easy to think about. You know, just think about these bonds that are, you know, an important part of our Hamiltonian, if it's, say, a Heisenberg model. There's a strong interaction between them. They want to form a singlet. So if we put them both in our small space, it can totally solve that degree of freedom and do a really good job. Okay, and then later on, they're not part of the space, but at least some point they're part of that space. Okay, and then when you do an SVD, you do an SVD on the little piece and turn it back into the matrix product state. Okay, so we never form the big guys on the edge, which are exponentially large. We just you know, use the fact that we can evaluate matrix elements for them for the Hamiltonian and put it together. And then we have the sweeping. Where it simply involves taking these 2 sites in the center and moving it back and forth. Location of the 2 sites. Okay, so what do we have? So this is essentially the DMRG algorithm. Density matrix renormalization group, or just say DMRG. The name is largely historical. It came out of Ken Wilson's numerical renormalization group as a way of fixing flaws when they're applied to lattice systems. So it was a natural name at the time. But now when you think about matrix product states, it doesn't tell you anything about the matrix product state language. So people just say it's a mysterious DMRG. Okay. So what happens when you do this is that you, in a sort of nice case, we can plot the position, say I, from 1 to n, and we can plot the energy, okay? And it'll start someplace high, so we start there, and it will just sort of zigzag down as we sweep back and forth, and then get very close to the ground state. Okay. So that's the basic thing that you see when you do a DMRG calculation. There's a lot of stuff going under the hood. But we make this zigzag path as we go through the system, and we're getting a better and better approximation to the ground state, and the energy is coming down. Okay, and it can be very interesting to follow that wave function as the energy decreases. A lot of people just look at the final answer and say, that's it. Now, you learn a lot by following how the system tries to decrease the energy, because it tries to put the most important things, it tries to fix them first. And so you may have something that, first tries to make all these singlets. You see that happen right away, but the energy is still not quite where it wants to be. And then it builds in correlations between them, and it slowly puts in successive degrees of freedom. It sort of fixes them. You can also get situations where the system gets stuck, okay? And so when you're doing a DMRG calculation and you're doing a simple 1D system, well, okay, it won't get stuck. But if you do it for a more challenging system, you'll find that it often gets stuck. And the way you get around that is to just really understand the physics of what's going on. It could be, here's an example of how it might be stuck. Suppose the ground state was a ferromagnet, and it had two choices, all up or all down. And you start it all up, okay? But you put a little tiny field that favors down, very small one. Okay, so it would have to tunnel all the spins at once to find the true ground state. It's never going to do it, right? So it'll be stuck, okay? So it's very, very easy to think of things that, it can get stuck. And another example, suppose the particles are attracted to each other. You have a system of particles and they're attracted to the walls. Maybe it's stuck on the left, or maybe it's stuck on the right. Okay, another thing that we had to deal with in sort of a practical thing is in systems like the Hubbard model, TJ model, we find that there are broken symmetry stripes that go in the system. Well, did the stripes run horizontally or do they run vertically? You just have to run two different calculations. They'll both be stuck. Okay, so I want to show a few slides from my laptop. If I can start things up. Okay. We may have here's a question of the difficulties of getting another system going, but, oh, and I want to see, it's all done on Zoom. Okay, so I may need some technical help here. Okay, so I've joined. Okay, so I want to stop sharing my screen. Okay, stop that. This guy's here. Share screen. Okay. How are we doing? Okay, so here's a few slides from a sort of easy DMRG calculation by today's standards. Okay, so this is for a spin 1/2 chain, 2,000 sites. Okay, so obviously challenging if you're going to try to do anything exponential. The parameter M, that's the bond dimension. I talked about the system sweeping back and forth and finding the ground state. So here's the results. This is the system, even for a finite system, the beta ansatz works. Okay, so we know the exact energy, that's with the stars. Okay, and you see the sweeping, it's 2,000 sites, but we're only going out to 1,000 sites, and that's just because it used a reflection symmetry. Okay, so we flipped it back when we got to the middle, and then that means in the middle, there's a vertical jump in the energy. That's on the right-hand side. That's where it sort of updated the right-hand side with the left-hand side that you just got and rediagonalized that. And that gave you a big jump in energy. So you think that that would be similar to the path, going across. All of that minimization just got updated to the other side. And then you sweep back and forth. Okay. And you can see it looks like it's getting very good. This is the error in the energy. It's the absolute error in the energy. Okay. And so, it's all relative to minus 900 or so. Yes, question.
Sorry, did you solve the 2000 side beta answer? So did you use a thermodynamic primitive?
2000 side beta answer.
That was probably harder than.
Well, certainly harder for me, right? I didn't know before I did this. I said, I can do it, with a finite system. So I wrote the code and did it. And it gives the first excited state. Okay, so that's the red line. This is the right-hand side, it's the error in the energy. And notice that there's curvature and there's a little bit of behavior change when it goes past the first excited state. So in the early stages, it thinks the system is gapless. Okay, and the entanglement, the corrections to the area law depend on whether the system is gapless or not. We'll get you in a second. Yeah. So once you're past the first excited state, then it thinks it's got a gapped system, and we see it losing some of its curvature. So, basically, there's some dependence on the sort of gaplessness or not, but even in this gapless case, we have this sort of exponentially good convergence. Yeah, good question. Pure Heisenberg, gapless. So that first excited state is proportional to 1 over L, 1 over the length of the system. It's open boundaries, but the DMRG, the size of the gap is also 1 over L in the periodic case. So that part isn't too different. Of course, the DMRG would do very poorly in the periodic case. In this case, we could do it. We could think of it as you can make a periodic system as just a 2-leg ladder, but not connected in the middle, connected at the first and last site. Okay, so it turns out that the performance of a system with periodic boundary conditions is the same as if you sort of doubled it up and connected it. And that's because the entanglement is cutting the system in two. And if you have a ring and you want to cut it into 2 parts, how much area do you get? Well, you cut off a chunk and it always says 2 edges. So you can see immediately that the area law tells you that DMRG wants to have open boundary conditions because the cut is only the area associated with one thing. Okay. And the area, of course, if you think of 1D, the area is always 1. Well, no, there's some sort of like correlation length in there. Something that's sort of telling what's going on right in that vicinity and some sort of accuracy trade-off. Okay. More questions here? Okay. X, Y, and Z. Yes. Yeah, same coupling. Oh, no, anti-ferromagnetic. Yeah. No. Okay. So a key point was that this idea applies to the ground state. Just sort of by thinking of the number of degrees of freedom, it couldn't really apply to the excited states. It's sort of interesting to have this picture in your head, even if you sort of understand it. First of all, so these are just the energy levels from an exact diagonalization of some short chain 8 and 12. Notice how sparse they are at the edges. Usually we're living here. We do some excited states, but we're staying down here. Okay. In the bulk, they get exponentially close together because the range is not increasing. The range of energy values is algebraic. And everything, the number of states is exponential. So they're getting exponentially closer together. These states, you can't even really think of them as being particularly physical because the uncertainty principle says you can't prepare them. The spacing between the energy levels is exponentially small. And so therefore it takes an exponentially long time to prepare them in any physical process, right? So, so mostly we don't think of these, but now let's look at these mostly topological states and say, what is the entanglement entropy? Cut down the middle, okay? And if it was really strongly classical, you'd be right along the bottom. The ground state is over there by the capital M. Can anybody, and oh, and the other thing I did was I added, so we can see each state individually, I added a little bit of random noise to the couplings. I think to a magnetic field. So what do you think these two states are over here? Zero entanglement. So by little noises split the all up and the all down. Okay, and those have zero entanglement. So the extrema, just flip the sign of H and you sort of see the same sort of behavior. The maximum entanglement that you can have, what you get from a purely random state is n over 2 log 2. The log 2 is just 2 degrees of freedom, spin 1/2. Okay, and you're cutting it in half, so that's the n over 2. And you see the sort of approaching that, and there's some extra symmetry in this that I think people actually study this in more detail, and it actually gets very close to the bound in more general cases. It's not in this one. Okay. Okay. This is, so probably some of you know some details about these spin systems. Again, purely antiferromagnetic Heisenberg model. So this is the entanglement entropy cut down the middle for the spin 1/2 system and the spin 1 chain as a function of the length of the chain. Okay, so I mentioned that the spin 1/2 is has a little correction to the area law. It's a log correction. So the black line is slowly growing, that's growing as a log. Okay, so you can see it's pretty modest. The entanglement entropy is very small compared to the maximum possible. And who can tell me what's going on with the red bump in the middle? This you have to know something about the spin 1 chain to understand. Why did the DMRG do this noisy bump in the middle? That is not very reproducible. Any ideas? Okay, so the spin 1 chain is topological. Asaki's back there, he knows this very well. So it has edge excitations. There's essentially spin-ons and they're free. And so do they talk to each other through the chain? Their interaction is exponentially small. So when you do a DMRG calculation with a practical cutoff, they lose touch with each other. They get pinned into a product state. So there's some extra effective, it's like an edge would be freer than the topological system, but it's just a spin 1/2. And it's sort of like, it'll be stuck up and down, and the entanglement will actually be less. But before that, if it's got a true exact ionization ground state, it's in the single. Or, there may be some even odd alternation, but in this case, it's so here it's sort of losing its accuracy to the single, but it's an exponentially small error in the energy. Okay. And so next time we're going to talk more about time evolution and 2D systems. But I wanted to show you one more sort of practical thing in a DMRG calculation. This one, in order to need it, it's for a 2D system. But this is energy extrapolation with the truncation error. And so I've emphasized that we control the matrix product state by this matrix dimension. But you can also think of it as when you do the SVD, what's the total probability of the stuff you threw away? Okay, so you threw away some singular values. The probability is the square of each singular value. You sum up the ones you threw away, and that's the truncation error. Okay, so it turns out that there's a close connection to the truncation error and the actual error in the wave function. You're working with some psi MPS, and you take psi exact minus psi MPS and square it. Well, this is related to it in a certain situation where if you started with an exact state and did one truncation. Okay, so you can extrapolate it just like you would do if this was a variational calculation. We have some error in the wave function squared, and we look at the energy, and so we can extrapolate to more accuracy. And this typically behaves very linearly. And so this is data where the extrapolation is based on the solid black curves, and you can then use it to extrapolate the energy. And then the further DMRG calculations are the red dots, and they follow along the line. Okay, so this is extremely useful. It sort of multiplies your accuracy by an order of magnitude. Gives you an error bar also because this size of the last extrapolation tells you something. And so you have some error bar. Otherwise, if you have just a variational state, it may be difficult to determine an error. The other thing that this will tell you is that if this doesn't look like a straight line, something is going wrong with your calculation. And it doesn't mean that there's a bug, but it may just mean that you started at some initial state that's rather far from the ground state. If you started in an anti-ferromagnetic state and it wanted to be ferromagnetic, it will have some trouble getting there. This is only the asymptotic when it's close. And so what you'll typically see in cases with a bad initial state is it'll come along for a while with a semi-straight line and then suddenly drop as it finds something else. Okay, and when that happens, we typically start the calculation over with a better initial state. We try to understand the physics of that, and redo the calculations. And it's still possible that someplace further down in the calculation there might be something that was a better state that we didn't find. That's always possible, and so that's what makes it still sort of an art instead of just turn the crank. Okay, so that's all I wanted to cover for this lecture, and I'm open for more questions.
Yeah, so we have a couple of minutes for questions.
Yeah.
First one, is it normal to change your bond dimension as you're going through the DMRG process?
Right. So first of all, there's a natural different bond dimension on the edge of the system. If you cut one spin off and look at that bond dimension, it can't get any bigger than 2 or whatever so there's a limitation on it. And so you're going to be working with a different bond dimension throughout the system in general. And then it's very natural to just control that. So we can put a truncation error cutoff as a control and let the bond dimension do what it wants. Or we can just slowly increase the bond dimension and track this. Or what we usually do is do a little bit of both. We don't want our system to crash or use way too much time. So we put some upper limit on the bond dimension, but then we also use the truncation error. And it's just, the first sweeps are very fast when you have a small bond dimension. Yeah.
I have actually how this small block, so it cuts the wave function into 3 pieces, and in the middle is a small piece. So the wave function for that small piece is that like chosen by diagonalizing the small function, which neglects the coupling between these 2 sides of the natural sides.
Let me see if I can pull up a little picture. This is some previous notes with different level of detail. Okay, so okay, so this is the form of the effective Hamiltonian. Okay, this funny tensor here. So the solid lines, those are 3 index tensors on the edge, and then 2 tensors in the middle. The middle of the system, that tensor comes from a representation of the Hamiltonian in terms of a matrix product operator. Okay, and this. So just quickly, the Hamiltonian, an individual term like SZ, SZ. In terms of diagrams, would look like this. These are all the identities that make Hamiltonian so simple. It's a sum of these. You can convert this to what's called a matrix product operator, where it just has this form with some long dimension that may be on the order of, say, 5 or 10 for a typical system. Okay, then you can find the effective Hamiltonian just by contracting the matrix product states around it. So here's our, so there's a little bit of some of the details of the manipulations of these that I skipped today. But we can, so there's simple rules for a very general representation that gives you the tensors you need to construct the Hamiltonian. And basically it's these sorts of pieces.
So it's basically the representation of J as I dot as I plus 1, but we're choosing the wave function of these 2 sides such that it minimize only this term.
So we're doing all of the terms summed together.
Oh.
Yeah. So the first thing we do when we make this matrix product operate is sum up all those pieces. So they're all in there together, and every minimization we do is of the whole system.
Oh.
Okay, but the beauty of it is that most of it is hidden. It's just sort of contracted away with tensors from the edge. And you're only looking at 2 sites in the middle with a limited number to be free, but it's a representation of the entire Hamiltonian. And it would not work nearly as well if you didn't do that.